Hello, everyone. Welcome. So today we're going to be looking at a very complex script, which is going to help you, give you some insights into modeling, into automating parking layouts. Okay, and for anyone new to this channel, please like and subscribe to our YouTube channel. It helps us just get the message of computational design out there. In my view, it's a very crucial tool in solving a lot of problems in the built environment, especially when you start combining it with other tools like AI and genetic algorithms, which this is about. But in this presentation, I'll mostly be showing you the logic of the script, and in the next one, because it's quite a complex and lengthy script, in the next session, we'll then run the generative design workflow. Okay, so as you can see on my screen here, I'm just going to expand this view. As you can see on my screen, we've got, I've divided the script into 3 parts. So the bottom here is where we define the parking patterns. This mid section here is where I've created this the part of the script that defines a bounding rectangle. You'll understand that later. And on top, we have the actual logic, the actual generative design logic. Yeah. So I'm going to start from the bottom and go to the mid section. I won't explain too much there. Yeah, there's so many other ways of doing this. Then on top, I'll explain the generative design workflow. Okay, perfect. So let's go right ahead. Right, so on top here, we have the first pattern, which is the non-interlocked parking bay pattern. And at the bottom, we have a herringbone pattern. And at the bottom, we have an interlocking parking bay pattern. So I'll show you how all these look. I'm just gonna get I'm just gonna get this input code block over here. Okay, I'm just gonna show you how they all look. I'm gonna run the script. Okay, so you can see this one is what I call the non-interlocking pattern, because the parking bays don't actually interlock with each other. Then I would move over to the next one. And I'm just going to show you that over here. Okay, this here. And you can see this one is a herringbone pattern. Okay. And in the next one, we've got the interlocking, what I call the interlocking pattern. Okay, so I'm just gonna, okay, so it's over here. Okay, and so that's the interlocking pattern. All right, so just so you know, this script has what I uses the Dynamo out-of-the-box nodes. It also has design script, which is what you see here. And then it also has some Python in it, right? So in the very complex areas has a lot of Python. That was the only way I could figure out how to do it. There was no other way, but I'm going to try to explain that. Okay, so I'm just going to explain the first pattern, which is the non-interlocking pattern, which is right on top here. And then the rest I'll just brush over, but I'm going to zoom into them so you can easily copy it if you wanted to make the script on your own. All right, so to start off, I've got the inputs here on the left-hand side of the script, and I've got a note here that says this block of the script creates the required parking patterns, including non-interlocking, interlocking, and herringbone patterns. Okay, so the parameters we've got, I'm going to zoom into them so you can see very clearly. We've got the parking bay width, we've got the parking bay length, we've got the parking bay angle selector. So number one, so let me just show the zoom to fit over here. Oh, sorry, I just need to show that, create an input again. So I'm just gonna add another input because I want to show you as I change the parameters what happens. Excuse me. Okay, I'm just gonna set this to automatic and zoom to fit. Okay, so just watch what happens when I change the parameters. Okay, I'm just gonna zoom in a little more. Okay, so when I change the parking bay width, you can just watch the pattern changing. Let's say we make it something like, let me just make it very big. Let's say 4,000. You'll notice here that the pattern changes there. Then if I change the length, let's say about 7 meters, changes as well. And the angle selector is basically what allows the parking bays to change from 45 degrees to 60 degrees and to 90 degrees. And this has been based on the Western Cape municipal bylaws, but these things are very applicable all over the world and easily modifiable. So if I make this 1, you see that becomes 45 degrees. And if I make it 2, it becomes 60 degrees. And when I make it 3, it becomes a 90-degree pattern. I'm just going to leave it at 60. Okay. All right. AJ, welcome. Welcome, Albert.
Sorry, I'm late, man.
No, it's all good. Welcome. No, you haven't missed much. I'm just explaining the parking patterns. Yeah, literally just started. Okay, so then we've also got a parameter that controls the distance. I mean, in the non-interlocking pattern, it controls the distance between the bays, and also we've got a parameter here I call the parking pattern selector that allows us to select between the non-interlocking pattern, the interlocking pattern, and also the herringbone pattern. Okay, so I just need to show you that. I'm just going to also, I'm going to move this input to the end here. Okay, I'm just going to run it. And if I start to change this parameter over here, you see here, that is the non-interlocking pattern. That is the interlocking. And this one is the mirrored interlocking pattern, and there's one for herringbone. Okay, so as I mentioned, I'm just going to be explaining the first one, how to create the first one, so we don't spend too much time. And then I'll gloss over the other ones. Okay, so as I also mentioned previously, this here is full design script. It just made sense for me to do it this way. I mean, I just wanted to have everything compact in one node. Okay, so I'm going to explain as I go through it. I'm going to be showing you the nodes that all these lines represent, so you can also fully understand what all these lines mean. Okay, so on top here, I've got all the parameters. I've got the bay width, the parking bay length, the parking bay angle, the bounding curve length, and also the island width, which is the distance between the parking bays at their center. Okay, so the first thing we have to do to create the pattern is to work out what the actual bay length is against a center line. So to explain what I mean, I'm going to show you here this diagram. So you see here, as the parking bay rotates, right? As it rotates at an angle, the width changes. So you need to understand, you need to be able to work out what that distance, you see that red line over there, that x underscore disp, you need to work out what that distance is against the center line. Okay, so to do that, we need to use this formula, which is the bay width and the cosine of the bay angle, okay, which is what you see here. So you see the angle here, and you see the width of the parking bay, and when you multiply those, and when you divide the bay width by the cosine of the bay angle, you then get that actual length on the red line. Okay, so the standard node that allows you to do cosine is math.cos cosine, dot cos. Okay, so but that has been reduced to that design script node, that design script text over there. Okay, so then the next thing we need to do is to calculate the number of parking bays that will actually be replicated along the pattern, along the line of the pattern. So there's a, which you'll get this later, but there's a line I'm getting from the bounding box, which is on the next level of the code, which is above here, right? So there's a line I'm getting from that bounding rectangle, and that gives me the length. So I basically divide that length, right? That curve length by the actual width, which we get on top over there, right? So that then tells us how many parking bays, you see when I replicate here, that need to be along that line. Okay, and the next step, we then need to create the line, which will be at the center. So when I input that in here, okay, but first I also need to take the, I'm going to hide this one because it's been rotated. Just going to hide this one over here. And guys, please feel free to ask questions if you're lost. Control C, Control V. Okay, I'm just going to get the pattern here. Okay, so there's a, just ignore that. So there's basically a line at the center here, and that's where they get replicated along. Okay, so then we basically make that line, so which is this line, but this other pattern has been rotated already, but you'll get it as I go along. And then I need to get the start point coordinate system. Okay. Then I then get the start point coordinate system's x-axis. All right, and then the bay, then I then get the bay line location points. So I'm just going to show this over here. Okay, so it's along these points, then we find that we finally place the parking bays. Okay, then to place the parking bays, we then have to create planes along those lines. So those planes, you can't really see them yet because they're quite tiny on the screen. It's those planes that the parking bays actually get transposed onto. Okay, and then afterwards we get a coordinate system. You need a coordinate system to actually transfer the bays onto, and then afterwards we actually then create the initial parking bay. So if you look over here, there's just going to be one rectangle. So it's this first rectangle that's going to be transferred onto those initial points you saw in the beginning. Okay. Then we need to get the start point of that rectangle. Let's copy this again. So if you look on this rectangle, we have a start point. Okay. So it's on that start point that we then move that rectangle to those points that were created initially. And then afterwards, we then transpose or transform the base onto those location points. So if you look on here, you see them. I'm just going to hide that initial one again. Sorry. So you don't get confused. Okay. So we've basically just created the first half of the pattern. Then afterwards, we're going to mirror it to create the full pattern. Okay. So then, sorry, I'm over here now. I'm over there. Okay. Okay. Then we then mirror the parking base, the parking pattern. Let me just show the first line again so you get what I'm talking about. So this line over here, that's in the design script. So you can see that line. We mirror the parking pattern along that line to create the full pattern. So when I show you these parking bays here, you will see what I'm talking about. So then I'm just going to get this in here and show you the preview. And then that basically is what then mirrors the pattern. So that first copy of the base along that line. Okay. And then we rotate it. The reason we have to rotate it is because when we run the generative design study, and I'll show you that when we get to the top of the script, we need to be able to rotate it around the parking area so the generative design study can test the best angle that allows us to fit the most amount of parking bays. Okay, so when I copy this again, when I copy that again, you can then see, and I place this in here. So you can see that other one is rotated around the center point of that line. Okay. All right, and this one, this code here creates an island, basically the spacing between the pattern, because usually with these kind of patterns, let me just hide this one here. Usually with these kind of patterns, sometimes you want to place trees between them. So I'm just going to show you that parameter. So if I make this about, let's say 2 meters, basically moves the pattern, spreads them apart. So it allows you to maybe place some sort of a planter between them. Yeah, and only this pattern allows that. Okay. And then the other thing we need to do is to calculate the overall width of the pattern. So that is done with this by multiplying the bay width by the sine of the bay angle. Okay. And that gives us the overall width of then we do some other math there that then gives us the overall width of the pattern. So this is important because when we replicate them and we copy them later along the parking area, that width is very important in us replicating it, or else it won't work out. Okay, very similarly to the above, it's a similar structure. We repeat everything on top there. Yeah, so this is just to create the herringbone pattern. So there are towards the bottom, some differences. So if you needed to, I'm just going to scroll past it. So in case you needed to copy it, you can just easily replicate it on your own. So there are some differences when you mirror it. You need to move it differently till it meets the right, till it fits in the right position. So that is for the herringbone pattern. And then here we have the interlocking pattern. I'm just gonna scroll past. And remember again, these are just in design script, but they're default Dynamo nodes, just written in design script. Okay. Yeah. So this is the section for creating the parking pattern. So a part that I did not mention here, which is in the beginning. So because the Western Cape's municipal and the parking regulations here allow for 45, so basically this 45 is 45 degrees, and this 30, just take it as 60. It's just the script here necessitated that I worked it out like this. So 45 is for 45-degree parking. In the regulation, this is 60 degrees, and here it's 90. So I'm working out, what I'm indicating is the angle of the bay against this line. Okay, so that the line, that face here, so basically what I'm talking about is this face, if you can see my pointer, this face of the bay against this center line. Okay, so you've got 30 and then you've got 0, which and in 0 would mean 90 degrees. Okay, so because we want generative design study to be able to select all these angles and play with them to create the during the study, we need to create something called a dictionary. So a dictionary accepts keys and values. So it's basically like your standard Oxford dictionary, where when you want to define something like, say, fruit, right? A fruit comes with a definition. So in this case, 1 is the key and 45 would be the angle. So basically when I say over here that I want the parking angle to be 1, it gives me 45 degrees. And when I say 2, it's going to select the 60 degree from the dictionary. And when I say 3, it gives me 90 degrees. So as you can see here, there's a dictionary. So dictionaries, their structure is usually not in any particular order. So this here indicates the key, and this indicates here the value. So you can see here, I have a key of 1, right? And the angle of 45. So it pairs them like that. A key of 2, angle of 30, a key of 3, an angle of 0. Yeah. And then basically when so this node here, and I've tried to put descriptions along here so you can just read as I go through. This node here, when I select that number here, is what allows us to pull the required value from the dictionary. So as you can see here, the current value is 2. So it gives us the 60 degree. But when I make it 1, it gives us the 45, which is, the 45 degree over here. So you can see the value changes. So when you're creating complex, scripts like this, dictionaries are very, very important, especially something that has patterns where you need to start switching between different types of data sets. I mean, switching between different kinds of patterns. And in dictionaries, I mean, in generative design, that happens a lot, where you have to switch between different types of things, so it's important to understand how dictionaries work. All right. Okay, so another thing to note is that dictionaries only accept, I mean, as a key, they only accept strings. And a string, sorry, if you look here, so you see here, the string. So the keys have to be strings. And then string means text. So you have to convert those numbers which are in here in this list two strings. Okay, so let's hurry along. Then basically after you've created all the patterns, so I made those 3 patterns, those, all those patterns over here. I then have to create more dictionaries, right? So when the parking pattern input, the selector is 1, I want it to give me the non-interlocking. When it's 2, I want the interlocking. And when it's 3, I want the interlocked 2. And when it's 4, I want the herringbone pattern. So all these, you can see here again, I changed it to a string, which means text. So I inputted that, I placed that input, those values, into the keys. And then the list of parking patterns I placed here into, so the parking patterns which are fed into this list, I place them in these values. Okay. So basically when you see here, when I go back to the beginning and I start to switch, but I have to, sorry, I have to hide this one. So let me just delete these so you can see what I'm talking about. All right, so I'm just going to show this one over here. Okay, so basically when I start switching between the patterns, okay, so this one, as you can see here, this is a non-interlocking pattern. Then when I go to the other one, which is the interlocking number 1, the other one interlocking 2, which is basically just mirrored, and number 4 is the herringbone pattern. So this value here is what allows us to then pick those different patterns using this dictionary. So this dictionary value at key takes that key, right, which has also been converted into text, and picks the required pattern, which is a bunch of rectangles, right? So they're all just rectangles, a list of rectangles for the base. So it picks that pattern, the required pattern, from the dictionary. Very important data structure to understand when you're trying to do these kind of things. Okay, and also I placed those widths that I mentioned that we calculated at the end into a dictionary. So it's the same thing. So just 1, 2, 3, 4, and I placed them with the same list structure. So I placed them, all those values, in that list. So this should actually be list of parking widths, not patterns. So when the same thing, when we switch between the kind of parking patterns in the beginning, it gives us a width. So that row width from end to end, from corner to corner. So basically from this point to that point, that is what we get. So of the entire pattern. So it's very important we have that, because we obviously want to copy this thing several times over the parking area. And you'll get what I'm talking about soon, very soon. Okay, so that is the parking pattern. So as I mentioned, this area here is just defining the parking pattern. This one here is about defining a bounding box that holds the parking area. Okay, and this on top here is the generative design script logic. Okay, so I'm just going to hide this and then just go over very briefly what this part is doing. Okay, so as I just added a description here, so this block of the script creates a bounding rectangle around the parking area. The bounding rectangle is used in laying out the interior parking bays. Okay, so the first thing I had to do here, just so you know, as an input from Revit, I get a field region. So it's that field region that the parking pattern gets laid laid on. Okay, so what I do there is I'm just going to show you a preview of the surface. Okay, so basically I've taken just this surface over here. So that one is what I've brought into Dynamo. Okay. So I've taken that surface, then I get the center point of the surface. I'm just going to go through this quickly step by step. So I get the center point of the surface, and I define a plane at the surface. At that point, if I show this, you're not going to see the plane. The planes are usually very tiny, even on Grasshopper as well. Okay, then I get the perimeter curves of the surface, and then I also get the endpoints of those perimeter curves. As you can see, those black lines there. So the point of this, the reason I'm doing this, getting these endpoints, is I want to project those endpoints onto planes that are located at the center of this surface. Okay, so I then get these things called rotation plane vectors. So these vectors, I get a vector y-axis, okay, and I also get a vector z-axis. So I use these vectors here to create two planes that are basically 90 degrees to each other, okay? And then on those planes that are 90 degrees to each other, I project those endpoints onto them. So I'm going to show you what I mean. So if I show you the preview here, and I show you the preview here, you can see that it is these planes, I use the extent of these lines, of those points, to define a box around this shape. It was just, for me, logical to get the box around that shape to then be able to define the area I need to place those patterns. Right. So this was pretty complex to work out, but yeah, I was pretty happy when I figured that out. So yeah, so you can just imagine in your head that a box gets formed around. So whenever I rotate the pattern, the box always fits the shape. Okay. And so then I do some other things over here to sort the point X and Y values. And then I check if the points Y values are equal. And then basically all this over here, so you can just easily copy this. So all this over here basically helps me then create that box. So at the end of this, I'm just going to go over this as well. So you can, if you needed to copy it, you can do so. Okay. Right. As I mentioned, there's many other ways of doing this. I've seen some other people do it differently. So basically at the end of this, what I get from it is a bounding rectangle that defines that basically holds the shape. Okay. And then when I just reveal this rectangle over here, you can see it holds the full shape there. Okay. So I'm just going to go to this over here. Let me just show you the angle. So when I start to rotate, you will notice that the shape is always fitting around the outline of the parking area. Okay, it never misses it. It's always touching it. So that lets us down the line set out our parking pattern. Okay. Okay. Feel free to reach out. If anyone watching the video does not understand, feel free to reach out, and I can maybe explain that if required, that part in more detail. But I'm just going to go over the main logic of the script now. Okay, so I'm just going to hide everything I've shown here, so then we can actually talk about the the important bits of the script. Okay. And as I also mentioned in the beginning, this session is about the logic of the script. It's quite lengthy. So in the next session, we will then run the generative design study. So, but here I want to explain in detail how we've come about generating the actual parking configurator. So as I explained here, this section of the script contains the logic for the generative design process, focusing on the layout of the interior parking bay patterns and the perimeter bays. It defines the algorithm and parameters that drive to generation of these elements. Okay, so the parameters we have here are the parking region. So this is what selects the surface, which is a field region from Revit. As I showed previously, it is that. So all these here, I'll show you how it works along those, on those, and the sent out line rotation. So when you rotate the pattern, the interior parking patterns rotate using this value. And this here is the level I want to place the parking bays on when I finally do load them into Revit. Okay. And this is here is the parking bay's concave corner spacing. You'll understand what I mean by the concave corner shortly. And also the parking bay convex corner spacing. You understand that as well. And here is the aisle type selector that selects between a one-way aisle and a two-way aisle. Okay. And over here, we define the perimeter aisle width, and this perimeter aisle width as a minimum will be 7 meters, because that is what's in the Western Cape Municipal Bylaw. When you have a 90-degree parking, the road has to be 7 meters minimum. Okay. So I'm not allowing for angles at the perimeter. I just made it simple. It gets super complicated to work out the math when you start adding angles at the perimeter. So I'm just making it simple for ease of explaining. And also the vehicle turning radius at the concave corners of the perimeter aisle. So you've got the concave corner, and also you've got the convex corner. So these are basically the internal turning radius, and as I show in the script here, and the external turning radius. And just to note, remember, and if you haven't watched the first generative design presentation on Dynamo, remember to always make these inputs. When you right click on your inputs and set them as input. If you do not set them as input, you're not going to be able to run generative design. So ensure to go back to that first video to watch if you haven't done so. Okay. So the first thing we have to do here, after we've selected just come over here. After we've selected the outline, the first thing we have to do is we need to use this data.remember node, which basically remembers that shape, that surface that you've gotten from Revit, even if you don't select anything when you run the generative design study. You cannot have any Revit geometry in your Dynamo script if you don't use this data.remember. It's not going to let you run it, right? And this I did explain in the first video as well. Okay, so then the next thing we have to do is get the perimeter curves of the surface. So as you can see over there, so that's the perimeter curve brought into Dynamo. Okay, and then the next thing we have to do is to pull that curve onto a plane, which is on the level that we intend to load the parking bays to in Revit. So if you look here, you can see there are two curves. You can see there are two curves over there. So what I'm going to do here, I'm going to show you. You see here, this is the roof apex level that I'm projecting it onto, which is from my Revit project. So if I made a ground story, it's going to project it to a different level, which is the base level over there. So if I change it back to the third floor, it's going to take it up to third floor. So that basically allows us to place it's going to, at the end, let us place the parking bays on the level we require. Okay. So this here is from the Clockwork package. It helps us get the level plane. This is the only custom package that we use in this script. The rest is out of the box nodes. Okay. So we get the level plane from this level. And then when you get the plane from the level, you need to use the data.remember node again, because it is a piece of geometry you're retrieving from a Revit object. Okay. So then we use that plane and we project those parameter curves onto the plane. Okay, so that is the first step. Okay, and the next thing we have to do there is to get the boundary curve vectors. So vectors, if you do not know what vectors are, I encourage you to go read the Dynamo primer, which was explained in the first video we have on our channel. So the Dynamo primer has, it explains a lot about geometries and what Dynamo is, and basically the basics you need to know to use Dynamo effectively. I encourage anyone to go read that. So you get the boundary curve vectors. That's what we have to do here. So, but the first thing we need to do is we need to get points at parameter. So these here, which you see here, 0 and 1, it's a list of numbers, 0 and 1. So what that means is I'm going to get the point at the first end and the point at the start of the curve and the point at the end of the curve. So in programming, even Grasshopper and Dynamo, all curves start with 0 and 1. No matter how long the curve is, the start is 0, the end is 1. Okay. The advantage of that is you can, no matter how long the curve is, if you have, let's say, 10 parameters from 0 to 1, no matter you can use those same parameters to divide any curve, no matter how long or what shape they have, right? So it's a simple way of engaging with curves, no matter their shape. Okay, I hope that was clear. And then, yeah, so we get the points at those parameters, which is the start and the end. And then we create polycurves from those points, right? So we have, if I open the list here, we have 2-point pairs, because you see in this list here, we've got 6 curves, and by getting the curve and the start at the end, so is that someone asking a question? No. We get the curve at the start and the end. So you see here we have 2 points, right? So if I show you the preview of this, oh geez, sorry, I just messed up my script there. Okay, so if I show you the preview, you can see the points get shown. That basically is the start and the end point. If you look here again, start and the end of that curve. Okay, let me hide the preview of that. Okay, so then we create a polycurve from those points. The reason I'm doing this is so we can get lines out of them, which you'll understand later. So we create a polycurve with this point and that point. So we then get 6 polycurves in here, okay? Because this has 1, 2, 3, 4, 5, 6 sides. Okay, and so from the polycurves, we then get lines. The advantage of lines is that we can then get the direction of those polycurves, essentially. Okay, then I flatten the list here. As you can see, the list here is very, they are sub-lists, but I wanted all of them to be on one list. And then from that, we then get a direction of those lines. So vectors, also the direction of the lines. We will use these vectors to work out the corner angles of the parking area. So this is where we start talking about the convex corners and the concave corners. Okay. So what we now want to do, the first thing here, is to pair the boundary curves with each other. So to be able to work out the corner angles, we need to be able to have curve pairs, right? So we then rotate the vector, the two directions, the two vectors of each of those lines around. That's what then allows us to get the angle. But I would, hopefully this is clear when I show you over here. So what I'm going to do is I'm going to hide this bit. I'll also hide this bit here. Okay, so let me show this preview. Okay, so we need to do something called shift indices. So what it means, it is moving, so from this original list here, it's moving what is at 0 to 5, and then what's at 1 to 0. So we're moving it around, okay? So when we shift those indices, we then need to reverse these curves, okay? Reversing it allows us to create the angle, to work out what the angle is accurately, okay? And then we need to create a list of the unshifted curves. So the original line list, which is this line list over here, with the new shifted line list. We add them into one list over here. Okay, and then we do a transpose, which basically combines the first curve in the first list with the other curve. Okay, so first 0 combines with 0, 1 combines with 1. Okay, so then that gives us curve pairs, which I'm going to illustrate now. So let me just show you, let me make an input. I say 0. So this basically means I'm getting the first item, the first value. So this 0, I'm getting it from this list. So when I plug this in here, you can see we'll have curve pairs. So you see here, curve pairs there. If I change this to 1 now, another curve pair, and I change it to 2, another one. So it is these curve pairs, we're going to use them with the z-axis at the center, at the intersection point, at the point where they touch. We're going to use them to work out what the corner angle is, right? Okay, I hope that is makes sense. So you're going to work out what that value is, and that's what's going to let us know if it's a convex corner or concave corner. What I think I should do is actually to change the surface we're using so it makes sense. I'm going to change it to this one, change here, because this one has concave and convex corners. Okay. Okay, so I'm just going to show you the entire curve. So you can see here, the convex corners are these corners over here, and the concave corners are these corners. So any corner that is less than 180 degrees is concave, and any corner that is above 180 is convex. But you should get this as we go along as well. Okay, so to then work out the corner angles, we got the line direction here from the original list of curves, right? And then we shifted the indices like we did previously, right? And then we took this original line direction and we plugged it into this vector input here. And then we took the reverse direction and we plugged it into this other vector, right? And then the rotation axis to work out the angle is the z-axis. So you see these values in here. So what I'm going to do is to illustrate to you what I'm talking about. Let's hold on. So I'll just make this scale about 1:500. Okay. So if you look in this list, we've got 69.05, which is that angle. Then we've got 235. Revit doesn't allow us to. Okay, if I do dimension, angular dimension, this angle in essence is if you work out those numbers, add those numbers together, that is 235. And if we do this one as well, that is 105. And that angle is 75. So as you can see, we've been able to use those vectors that we've gotten from those lines to work out the angle at the corner of the parking area. Okay, so that is pairing the corners, the corner curves, and also that is working out the corner angles at the parking areas. All right, so then the next part here is we need to, the way we are going to sort, sorry, I need to escape here. The way we're going to sort those lines and the corner points is to create a Boolean list that checks if the angles are greater than 180. So this Boolean, here is basically asking, because we've inputted those corner angles. So you see these corner angles we got from here. We're then taking them in to this list. Okay, so it's asking, is the corner angle greater than 180? If it is, if it's not, it's going to give us a false. So as you can see here in this list, if I just go back down, you'll see here 70, 69, 235. So the first two are not greater than 180, so they are false. And then the other one with the 235 is greater than 180, so it's true. So anything that is greater than 180 is the convex corner, as I explained, and anything that is less than 180 is the concave corner. So this is a very crucial step in us starting to set out the perimeter parking base. Okay, so then we use this Boolean list to sort the convex and the concave paired curves. So what I'm going to do here is I'm just going to hide this over here so you can see what I'm talking about. So I'm going to take this over here. So in this in list we have, so anything that is true goes into in, and anything that's false goes into out. So in this in list here, just let it run. All the convex corners, and which there's only one, it seems, if we look in the Revit. There should be about two. Oh, sorry, because I only took, my input only is at the index of 2, that's why. Okay. So basically all you see here, all the convex curves, the curve pairs get put in the in list, and the concave ones get put in the out list. Yeah, so you see here, those are the pairs, but it takes the whole thing, but you see those are the pairs there, that pair as well, this pair, and that pair. Okay, but it's not as clear as the first one. It will be more clear when I do this. So I get the first one, okay, and I take the one at the index of 1. I take the other one at the index of 2. You see, so that is how we've used the angles to sort out those corners. All right. Right. Then the next thing we had to do here is to sort the corner points, the convex and the concave corner points. So the first thing I had to do here was to get the endpoints from the original lines. Okay. Then I used those endpoints. I sorted those endpoints using this Boolean list, just like I did for those curve pairs, those corner curve pairs. Okay. So basically we just have, if I look here in the preview, we just have sorted lists of corner points. Okay, nothing much to see there. And then we sort the convex and concave angles as well. So you can see here in the in list. So the in, as I mentioned, is the convex. So you see all the high numbers, which are above 180, get sorted here, 235, 215, 245. And the out list, which is the concave corners, get put into the out list because they are less than 180. So they are the concave corners. Okay. So the next thing we had to then do is to create the, so I have to show you the, let me just show you this again. So the next thing we had to do is then along the convex corner, the paired convex corner lines, which I then got from here, okay, in the in list, we had to create the first set out points for the perimeter base. Okay, so if you see here, I show you the preview. I have to make this the parameter greater. So if you look at this parameter, convex corner spacing, let's say I make this about 5 meters. You can see it clearly. So you can see here from that corner, from each of those convex corners, we now have 2 points over there and 2 points over there. So it's from those starting points, we then start to set out the parking bays along the perimeter. So the more difficult thing to work out is the concave corners, because if you do not set those correctly, I mean, at the convex corner, the parking bays are never going to clash. But if you do not set these out correctly, you can imagine they start to clash with each other. You can't set out the parking bays at the concave corners from the starting point there, or else they meet each other. Okay, so I'm going to show you what I'm talking about. So if you look in this diagram, I'm going to explain this piece of design script in this diagram. I have these values over here, which just describes the complexity of working out this corner. So I have a parameter here called the concave corner spacing. So that concave corner spacing is basically this line you see here that separates this rectangle from that rectangle at the concave corner. So if you look here, we've got that input. We've got that input called the concave corner spacing, right? And we also have these values here called the base length, side length, hypotenuse length. Okay, so to work out this distance, so we need to work out all of these, right, to then calculate this overall offset from that corner. Okay, so to work out all of these, the first thing I had to do here was to get the angle at this point here. So you see this red here. Okay, so obviously we already know the concave corner, which we worked out previously, which is here. So the angle here is the same as the angle here. So you need to bring out your high school trigonometry when you're doing this. So this angle here is equal to this angle here. So to get this angle here, what I can then do is go say 180 minus concave angle. Okay, so the concave angle, remember we worked it out, then divided by 2. So when we divided by 2, I then have each of those. Okay, so this is important because I need to use this angle to work out this length, which is the side length. Okay, So to then work out the side length, we use this formula called the concave corner spacing. So which is that length here, which we know which is a parameter that we can play with and we can change if we wanted. We can make this 5 meters if we wanted, but at the moment I have it as 300. So the concave corner spacing multiplied by the sine of the equal angle, okay, which we worked out on top. Okay, then divided by the sine of the concave angle. So this is when you're working out an isosceles triangle, which is what I wrote over there. So it's basic high school math. That is what then gives us the side length. So that side length over here is the first distance I've then worked out. Okay. All right. The next thing we then need to work out is the base length of the triangle. So which is this length here. So you can see there's another length. There's another triangle over here. Okay. So with these things, you need to learn how to dissect geometry into like the bare bones, so to be able to get what's going on here. So we need to work out what that is over here, okay? And to work that out, what we've done is to go and get the 90 minus the concave angle, right? The tan of 90 minus the concave angle and the parking bay length. So you can see here, the parking bay length is this, right? This length over here. And then we also need to use, so when 90 minus the concave angle, which is this here, gives us that. Okay. And then that then allows us to work out that. So the last one we need to work out is this one, which will then give us, when we then add all these together, it will give us this overall length. And remember, these are equal, right? If you cut a center point here, they are equal on both sides. Okay. All right. Okay. So then the last thing we then need to do is to calculate that. Oh, sorry, I kind of skipped a step there. To calculate that hypotenuse length, which is the hypotenuse. It's the hypotenuse because it's opposite that 90 degree. Okay. So, yeah. So it's this over here. So we then need to work that out using this formula, which is the parking bay length divided by the cosine of 90 minus the concave angle. Then we then add all these three variables, which are that, and that, okay, to then give us the overall length. Okay. So at each of the concave angles, the offset is, this one is 10 meters, that's 10, that's 5.5, 9.3, and 11.2. Okay. So this is basically this was the most difficult part of it to work that out, because we had to work out 3 different values to get the overall length. Okay, so now that we've worked those out, we then go on to this part. And so just so you know, I'm talking about this top part first, which is about the perimeter base, and the bottom part is about the base in the middle. Okay, so now that we've worked this out, we can then use this to set out the corner points, the set out points at the concave corner. So if I show you a preview over here, you can see here now that we have corners, 2 points at the convex corners and 2 points over here at the concave corners. So when we set out the perimeter parking bays here, they're not going to clash. Okay. All right. Okay, so the next thing to then do here is to pair the set out points for the perimeter parking setout lines. Okay, so what we first need to do is to get all the indices of true and all the indices of false, okay, from the original list. So from the original Boolean list. So if you look at this Boolean list here, we're getting all the indices of false. You see, false is the concave, and all the indices of true is the convex. We need to get those indices because it's going to let us sort those corners back together, because we need, at the end of the day, to put them back together to be able to create those perimeter parking bays in a logical way, right? So we get all those indices you see here. So these indices, I'm just going to move this up. So you see all the trues, which are the convex, are 2, 5, 7. Then all the indices of false are 0, 1, 3, 4, and 6. Okay, so we then plug those together. So we plug in the indices together using a list.join. Okay, so list.join over here. So you can see here it's in a not ordered as yet. And then we also then put those corner points together. So the convex and the concave corner points, so which are over here in this list and also in this list, you can see. And as you can see, we have 5 pairs here. And we also have, as indices, we have 5, 1, 2, 3, 4, 5. Same thing, 3, and we also have 3 pairs. So they have to match, okay? So then afterwards, what we then do is then use these indices, which are currently unordered, to resort these numbers, resort these points, these corner points. Okay. Okay. And then the node that allows us to do that is list.sort by key. Okay. So the keys are the indices that we've got, and the lists are those corner points. Okay, so now that we've sorted them, we can then start to actually place those perimeter parking bays. Okay, so but to do that, let me just show you something over here. So I'm just gonna get an input code block by double clicking left mouse canvas. I'm just gonna put that in here. So you just notice what happens when I click on each indice, each point. So if you look here, they're not ordered the correct way. So what should happen is it should go 1, 2, 3, 4, 5, 6. But what happens is, you can see it starts from 0 there, and it goes over there to the next one. Then it goes to 0 here, and it goes over to this one. Then it goes to this one, and it goes to that one. So what happens, that is not ordered. We wanted to move along the perimeter in a logical way, along the flow of the curve. So to do that, we have to reverse the positions of these values, of these points. What I'm going to have to do here is to reverse the positions of these points, right? I'm going to have to reverse their positions using this list.reverse, which I've done here. Okay, so I'm just going to hide this one, and I'm going to reveal. Okay, so if you look on this one here, it should now be in the right order. So you see here 0, 1, and you see, and there, it's now going in the correct order. And correct order. So now we can actually use that to start to sort our parking bays. So I flatten the list, okay, and then I shift the indices. Okay, the reason for shifting the indices is because I actually want to pair this point and that point. But at the moment, these are paired together. Okay, so I need to be able to pair the lines along, the points along these lines together, so I can actually start to sort the perimeter. So when I flatten this and I've shifted the indices, it then allows me to pair those points together. So I need to show the preview. Okay. So when I show you this, if I click on 0, excuse me, click on 0, you see there, I click on 1, now it's together. If I click on 2, there, I click on 3, you see. So now, when I chop the list, what chop does, it basically cuts the list up into smaller bits. I can now pair those curves together, those points together. Okay, so I'm not showing the preview, that's why you can't see anything. Okay, so when I pair them together, you see that. Now they're paired together. Now they're paired over there. And now they're paired like that. And now they're paired. So now the next step is to actually create curves between them. Okay, so this here creates those curves. So I create a curve between there and there, a curve between this one and that one. And after creating those curves, those polycurves, you can't really see the preview now, and then find out what the length of those polycurves is. Okay. And then after finding out what the length of the polycurves is, I then use the width of the perimeter parking bays, the width, right? And I then divide the length of those lines. So that when I divide the length of those lines by the width of the perimeter parking bays, it lets me know how many parking bays have to be placed along those lines. Okay. All right, so that is this formula. Set out line length, which is these lengths. I plug them in here, and the parking bay width. Okay. All right, and then to be able to divide the curves the right way, I need to add a 1, okay? Because the number of points have to be 1 greater than the number of parking bays. All right, so then if you look at the values generated here, they are in decimal places, but we can't have decimals, right? It needs to be whole numbers. To divide something, it has to be integers. So to do that, we use a math.floor, which gives us the closest lower integer. Okay, so that is 46, 19, 24, 43, 24, right? And then I use a code block over here to then generate parameters. And as I mentioned, every curve starts from 0 to 1. Okay, so then we have parameters ranging from 0. This is a range in Dynamo. So from 0 to 1, I want these many parameters along that range. Okay, so then it gives us a few parameters from 0 up to 1. Okay, we then use those parameters to split these n curves into smaller curves. You won't be able to see it because they're all on the same, in the same place. And then, okay, from those split curves, we can then have center points. So then you'll be able to see this. So if you look in the preview here, we now have points over here. So these points are now basically the center points of each of those parking bays, perimeter parking bays. Okay. And then we then use those, we use these, let's see over here. We use these polycurves, and we get the coordinate system at their center points. So the purpose of getting a coordinate system is so we can get the x-axis. The coordinate system is what's going to let us move the points, in an x direction, which is relative to those boundary curves. So we can then move those those edge curves along that x-axis. So then I'm going to show you what happens. So we get the x-axis, and then we have to reverse the vector so it doesn't go outside of the boundary. And then when I show you here the translate, we need to translate. Translate means to move the points. So that is parking bay length divided by 2. So when I basically translate those points and I show you the preview, they get moved in by half of the parking bay length. So these center points then become the center of those perimeter parking bays. So this is a crucial step that we've gotten to here. Okay, so now we can actually we can pretty much do the final thing here, which is adding the perimeter parking rectangles to those points. Okay, so but the first thing we then do here is we get the length of each of those split curves. You know, you can't really see them, right? But there are curves there that we split initially. So we need to get the length of those curves because that needs to be inputted into creating those rectangles. So that is used as the width, okay? And then we create planes at those points we've created here. So those planes, those points here, we add planes to them. Those planes will host those parking bay rectangles. Okay, and then we create the initial rectangles. So, but what you notice when we add those rectangles is that they are not in the right order. I mean, they're not facing the right direction, right? They are disorganized. They're all facing the same direction, you can see, which is, you know, vertical, which is the default, the default way they're created. But we have to rotate them so they can face the right direction. Okay, so to rotate them so they face the right direction, we need to get we get polycurves from those edge curves. Okay, so these here represent those boundary curves. Okay. Okay. So we need to get the curves from those polycurves, which are lines. And as I mentioned previously, lines let us get their directions. Okay. So the directions are vectors. I open the list. So vectors, you can't see vectors. Okay. And we flatten the list of vectors. Then we work out what the angle of those vectors is against the x-axis, using the z as kind of the vertical axis. So we rotate our vector against the x-axis. So that then gives us an angles. So kind of what we did previously to work out the angles at the concave and convex corners. And then we use those angles to rotate our parking bay perimeter rectangles. Okay. So then when we rotate them using those values, which is, you know, we got the geometry, which is the initial geometry here that we created that's not rotated correctly. And then we get the vector angle about axis, which is this value here. We use that as the angle to rotate. And the base plane is the planes which we placed at each of those points. And then we rotate it, and then they get placed correctly. As you can see, they are now all correctly placed. All right. So that was a very long process just to get this. It's a very complex geometry, a very complex geometrical problem. Okay. So the last bit of this is the internal parking spots. Okay. To get the internal parking spots, we first need to create a surface area from, if I show you here, you see that gray zone? We created a surface over there. And then we offset that surface inward. Okay, so I'm going to hide this preview. Okay, so to offset that, we need to know what the parking bay length is. So obviously it needs to be beyond that, this parking bay length. So this parking bay is offset in, and then we need to offset again by the aisle width, which is the perimeter road. Okay. So if you look here, we offset it. So if I show you the preview here, so we then offset inward like that. All right. And then we then need to also add the turning radius. So this one here is the concave corner turning radius. All right, you can't really see it here, but I'm going to hide this preview. So you can see here, there's a curve there. This is very important because it's going to help us remove some bays at the end, because you don't want some bays within the turning radius of the car. So as the car turns, there's a minimum turning radius there. And then we then need to add the turning radius at the convex corner. So I'm going to hide this. As you can see here, there's also now a turning radius over there. So let's say I just go so you can see it more clearly. If I go back to our inputs and I change the internal turning radius to like 9 meters. Okay, and that this one I make like 10 meters. Okay, so you can see here we've added that turning radius. Okay, absolutely key for cars to turn, and it's to make your parking count realistic. Yeah, you would need to filter out any parking bays that overlap or go over that line. So that's why it's critical to add this. Okay, so after that, what we then need to do is create an internal surface from that outline. Okay, so now that we've created that, the surface from that outline, we need to create the perimeter roadway surface. So that roadway surface is created by subtracting this internal surface from the overall surface. Okay, so I'm going to show you that. So when I show you the preview, so the input here is this, which is the internal surface, and the other surface, which is the original surface, which is here, the overall parking surface. So that then gives us that perimeter aisle, right? So that's where the car is going to drive around the perimeter of the parking. Okay, and so we then start to jump into a bit of Python. Okay, so this is a simple Python script here. If you don't use Python, I completely so we have the input here, which is an angle selector input, IN0, and when we have an aisle type selector. Okay, so those get plugged into these inputs here that you can see, in0 and in1. And then what we have here is staple Python programming is conditional statements. So what this is saying is if the angle selector is not equal to 3, and mind you, this is based off the municipal, Western Cape municipal regulations, which I'll show you in this diagram. So if it's not equal to 3, the angle selector, and the angle selector for the angle for 3 is 90 degrees. So if it's not equal to 3 and the aisle type selector is equal to 1, so the 1 is the one-way aisle, which is the one-way traffic, I want the aisle width to be 4.4. So that this is what the municipal regulation says. So if you're in another country that has different regulations, you can easily just change this. It's usually not recommended to hard code like this. So maybe this could be in an Excel file, and you can easily just change it so the generative design script picks from that file. That is also possible. And then the other one says if the angle selector is not equal to 3 and the aisle type selector is equal to 2, which means if it's two-way traffic, I want the aisle width to be 5.4. And this basically is the condition when the aisle becomes, when the parking is at an angle of 90 degrees. When it's 90 degrees, for the cars to turn properly, the road has to be 7 meters. So that then gives us 7 meters. So this is a simple Python conditional statement that lets the generative design study pick these values. Okay, so as you can see here in this diagram, you can see here 70 millimeter minimum when the angle is 90 degrees for 90 one and two-way aisle width. It doesn't matter if it's a one side, you need to have, if it's one-way traffic or two-way traffic, it has to be 7 meters if you have a 90-degree parking. If you have a 60 degree, it has to be 4.4 meters. And when you have, what's it, 45 degrees, sorry, 60 degrees is 5.4. And one way, 60 degrees is 4.4. One way, 45 degrees over here is 4.4. And 45 degrees over here is 5.2 for two-way. Yeah, so this was based off the municipal regulations, right? So it, it's very important, or else it's just a waste. Okay, so the next thing now we need to do is to create the parking set-out lines. So initially, the previous step, I showed you this curve here, preview, which is basically a line, a rectangle that wraps itself around the internal curve. So let me just show you the initial line here, the initial curve offset. So it's always going to touch that line, you see. So no matter how I rotate, if I change the rotation angle, let's say I change the rotation angle to about 180 degrees or something, there's still going to be the size, it's still going to hold that outline. You see there? See? To the full extent. So this is important because we're going to use this rectangle to sort out the internal base, right? Okay, so when I hide, let me just hide this original offset over here. Okay. Okay, so what we do here is we get the curves from that rectangle, and I want the one at index of 1, which is that one there, and I want the one at index of 2. Okay, so I'm just going to hide this original one over here, so it's not in our way. So when I get the one at index of 1, so they're basically the ones that are parallel to each other. Okay, I then reverse the first one. The reason for reversing the first one is so the point I add to them are in the same, move in the same direction. And then the pattern width divided by 2 is, I then need to create an initial point along the first one that allows us to start setting out the pattern. So when I show you here what this is, you see, there will be a point along this one. You see, okay, there's a point along this one, you see? So that is the parking pattern divided by 2. So the parking pattern basically then starts getting set out from that first point. Okay, all right, so that is that node. Okay, so then to start setting out the other ones from that point, I need to go, say, parking pattern width. And remember, the parking pattern width comes from the parking patterns, which are way at the bottom of the script. Okay, so they get plugged in from this dictionary. Okay, we get it from that dictionary, as I explained previously. Okay, so I plug that parking pattern width and the aisle width, right? The aisle width we're getting from that Python script that I explained here, which is based off the municipal regulations. Okay, and then I start adding points from that first point over there. Okay, so now we know we have the parking pattern plus an aisle width between each pattern. Okay, and then after that, I remove the point at the index, the first point, because what happens, it adds, if you look here, it adds points on either side of this point, but I don't want the first point. So I'm just going to remove that first one. So I'm going to show you this list. So it's then, so I then get left with the one from that point outwards there. Okay, and then I use this node called geometry.closest point to add these points to the other one. And because they're parallel to each other, you will always have the points in the same place. Okay, so that is, we will then use this to start to set out our internal parking bays. Okay, so when we do that, we then add this point here, which the closest point to, which we projected onto this curve, and the initial curve here, the initial points on the other curve. We then create a list, and then we transpose. Transposition means, which we explained previously, to pair the first point in the first list with the first point in the second list, right? And second point in the first list and the second point in the second list, and so on. We put them into pairs, right? And then we create polycurves by points between those 2 points, you see. And so when I show you the preview here, it then creates those lines. So it's on these lines we will start to then place the parking bays at the center of the layout. Okay, and so yeah, we're nearing the end finally. What is this error I'm getting? Okay, we'll sort that out later. Okay, so right, so then the next thing we now have to do is to transform we need to transform this the packing patterns onto these lines. Okay, but the first thing we need to do is to get the center points of the internal parking setout lines. So if you look here, preview, we get a center point along each line. So we will take that parking pattern and throw it onto those lines. And by the way, the parking pattern is defined by this length between here. Okay, so that's what makes it accurate when we throw it on here. Okay, and we create planes at those points, and we create coordinate system at each of those planes. And then we create a coordinate system, the same thing, at the center line of the pattern. And then we also create a plane at the center of the pattern, and we create a coordinate system at those planes. We then use that to transpose, what we call transform, the pattern onto those lines. You can see, so here we have the herringbone pattern, and it gets transformed onto those lines. So if I then start to play with the original pattern, if I go back here, you see here, if I start to change the pattern, because we've placed all the patterns in a dictionary, it lets us change between each of the patterns. See, okay, so remember we have those 4 different types of patterns. All right, so that is transforming the pattern onto those lines. Okay, so then what we have to do here is to rotate, you know, in case we have, I'm just going to hide this so it stops looking confusing. In case we have, we switch between the one-way or two-way angle. When you have a one-way or two-way, you have to actually rotate the pattern. Okay, so I'm going to end soon. We have to rotate the pattern so it actually allows the car to move in either direction. So we have to rotate the pattern with this node. So we basically feed the original pattern in here, and we use this Python script, which I'm wondering why it's giving me an error. Just going to look in here, line 33. So essentially, what this Python script does is if we have two-way and one-way parking, it's another complex part of the script. But all the different types of patterns, basically for the interlocking number 1, interlocking 2, and the herringbone, for the when they are one-way or two-way aisle, the essential logic here is whenever those parameters change in the beginning of the script that allows for the one-way or two-way, this Python script here takes those patterns and replaces every second one with a new pattern, which then allows, if you can imagine it, it then allows cars to move in different directions. All right. So that is basically what it's about. So I can just show you when I run let me just make this an automatic run. When I change just watch the pattern closely. I'm just going to zoom in here. When I change the direction here of the aisle type selector, so this is a two-way. When I change to one-way, every second one should change over here. I think that's what's giving the script an error. Okay, so we're just going to keep it as one-way. There's a missing code at the top of the script that's making it malfunction. Okay, but essentially that should change it to two-way or one-way. So it should change every second pattern. Okay, then afterwards, what we then do is we filter the parking bays using this node here. We create a Boolean list of true and falses like we've done previously. We use this Boolean list to do something called filtering by a Boolean mask. So that then gives us in an in and out list, it lets us get the parking bays that intersect with the internal parking area. Let me hide that. Okay, so when we create this Boolean mask, you can see here, it shows us everything, but they've actually been sorted. So when I hide that, and you see here, I only pick the ones that are in, and I go to, and I show you this preview, it now only selects the ones that are visible, that are intersecting with the internal area of our parking design. Okay, so we then need to, as you can see here, there are some still intersecting with the aisle over there, right? Which we do not want. Okay, so what we then need to do is check again, which parking bays intersect with the aisle? So we get another list of Booleans of true and falses, and then we then sort them again by the Boolean mask. Okay, so then I'm going to hide this one. So when we then take the list that are the ones that do not intersect with the aisles, it gives us the actual parking bays at the center. As you can see here, that's now a clean list. And if I show you the ones on top, now that's a complete parking layout. Okay, so the next step for here is to actually work out, which is important for generative design, because the goal at the end of the day for something like a parking layout is to get the most amount of parking bays. So we then need to get the count of the perimeter parking bays and the count of the internal parking bays, and then we add them together using a list of count. We work out how many they are in this flattened list, and we then add the perimeter parking count to the internal parking count, and that then tells us how many parking bays we have. So that is the end of this one. And in the final, as a final thing, in the next stage, I will actually run in the next video, I'll actually run the script to optimize for the most amount using the Revit's genetic algorithm, the refinery genetic algorithm, to then tell us what angle and what pattern gives us the best amount of parking bays and the highest number of parking bays, because that is the goal when you're doing parking layouts, to give the client the best bang for their buck, right? So yeah, that's about it. So what I'm going to do now is I'm just going to test it on multiple shapes just to show you how it looks. So this one, obviously, it only has concave corners. But what if we have different types of surfaces? Okay, you see this one. So it's a much bigger surface, so it's going to take a little longer. Okay, so we look at the preview over here. So obviously a current limitation is the parking bays don't always look like this, right? They always have entrances and usually have like roads going between them. So that is still a thing that needs to be added here. This is just a basic layout, you know, to get to the basic layout, but there's still steps to be added. So hopefully in the next video I'd have gotten there. So this is one you see here. There's lots of concave and convex corners. No problem, it works. If I change it to another one, change it to that one, which is much simpler, works, no problem. So any situation, as long as the perimeter curves are straight and you can work out angles. For curves, that will be a different script. But usually parking spots, I mean, the parking layouts, they usually, for what I've seen, they're usually like straight. So yeah,